Hello, this is Mr. P, and today we're going to learn about rational functions. Rational functions occur when you have a ratio of two polynomials. So you'll have a polynomial divided by another polynomial. That will cause a rational function. And some things that might come up during rational functions are vertical asymptotes and horizontal asymptotes. And we have a definition here of those. We would say that the line x equals a, and remember that x equals a number would always be a vertical line, and y equals a number would be a horizontal line. Well, the line x equals a would be a vertical asymptote of the graph f of x if as f of x approaches infinity, and that arrow means approaches. So f of x approaches infinity, or f of x approaches negative infinity as x approaches a, either from the right or from the left. So as you get closer and closer to that x value, the graph either increases without bound or it decreases without bound. Or you could have y equals b would be a horizontal asymptote of the graph if f of x approaches b as x approaches infinity or x approaches negative infinity. This would be the right side end behavior, and this would be the left side end behavior. What happens as you go to the far right or to the far left. And if the graph approaches a single number, then that would be the horizontal asymptote of that graph. And our most basic rational function is one that we've seen before as one of our parent functions. It's the reciprocal function. And we'll take a look here. This is the graph of the reciprocal function. It's f of x equals 1 over x, or in other words, y equals 1 over x. And we can see we have both of these ideas in this graph. Notice how if we take x equals 0, then we know we can't divide by 0. That would cause a vertical asymptote, because that graph is never allowed to touch that y-axis. But if we think about this logically, if we look at the branch on the right, then as x becomes smaller and smaller but still remains positive, in other words, it's approaching 0 from the right, then 1 over a very small number is going to be a very large number. So as x gets smaller and smaller, y gets larger and larger. Likewise, as x becomes a very large number, 1 over a large number is a very small number, so the end behavior to the right, which would be the horizontal asymptote, is x is going to approach 0, or f of x is going to approach 0, the y value will approach 0 as x goes off to the right, which we say approaches infinity. So to the right, the value of the function gets very small, and then as you approach 0 from the right, the value gets very large. And the left branch is the exact same thing, exact same idea, except you have a negative in there. So 1 over a negative number is still a negative number, and the same analysis as far as a large negative versus a small negative number still applies. And so this graph has both a vertical asymptote with the line x equals 0, which is the y-axis, and it also has a horizontal asymptote with the line y equals 0, which is the x-axis. And notation-wise, we talked about from the right or from the left. There is a notation for that you should be aware of, and it would be written as this. X approaches a, and then that little plus sign means from the right, from the positive direction. Or x approaches a, and then the little negative sign means from the left, which is the negative direction. So x approaches a from the left, or x approaches a from the right. All right, let's look at some of the things that we can analyze here. First of all, we want to be able to find these vertical and horizontal asymptotes for more complicated functions than just that reciprocal function. So let's look at, if we have in general, f of x is some polynomial that we're going to call the numerator over some polynomial that we're going to call the denominator. And this would be the generic form of the polynomial, where n of x and d of x have no common factors. So we're not going to be reducing this at all or simplifying it. Then there are a couple things that we can say. First of all, the graph would have vertical asymptotes at the zeros of the denominator. So any value of x that causes the denominator to be 0 would result in division by 0, which is not allowed. So that would be a value of x that is not allowed to exist on the graph. That's how we get a vertical asymptote. And then secondly, the graph will have at most one horizontal asymptote. It might not have a horizontal asymptote, but if it does, it'll have at most one of them. It could have any number of vertical asymptotes, depending on its degree. But it'll have at most one horizontal, and we find that by comparing the degrees of the numerator and the denominator. Remember, the degree is the largest exponent in the polynomial. So with our comparisons, the first one would be if the degree of the numerator, or lowercase n is the degree of the numerator, and m being the degree of the denominator, as we can see up here. These are the leading terms. So n is the degree of the numerator, m is the degree of the denominator. So if n is less than m, or in other words, the larger degree is on the bottom in the denominator, then the graph will have the line y equals 0, which is the x-axis, as its horizontal asymptote. We saw that in the last example. And that's just basically saying if your exponent is larger on the bottom, then as x gets very large, the denominator will grow quicker than the numerator. So you'll end up eventually getting a smaller number over a larger number, which will eventually approach 0. And then our next comparison would be if the degrees are the same, then the graph will have the line y equals a sub n divided by b sub n as the horizontal asymptote. And basically that's just saying it'll be a ratio of the leading coefficients. Notice this is a sub n is the leading coefficient, b sub n is the leading coefficient of the denominator, and it's simply going to be y equals, because it's a horizontal line, so it's y equals the ratio of the leading coefficients. And the last one, of course, for the comparisons is if n is greater than m, then there's going to be no horizontal asymptote. That's because as x gets larger and larger, then the numerator will increase faster than the denominator, so the value of the function itself will go to infinity, or in other words, increase without bound. So therefore, there's going to be no horizontal asymptote. There's no single number that it's going to be approaching. And these are generally the most known ones. There is actually one other. It doesn't result in a horizontal asymptote, but it does result in what we call an oblique asymptote. And if the numerator's degree is exactly one more than the denominator's degree, then the graph will have what we call an oblique asymptote, or some professors like to call it a slant asymptote. So the oblique or slant asymptote will be a line that is neither horizontal nor vertical that the graph will approach as you go to the far right or to the far left with its end behavior. Okay, let's look at some examples of this. And we're going to start with this example. We're going to find the horizontal and vertical asymptotes for this function. Notice how we have a polynomial. Even though it's a single term, we can still consider it a polynomial over another polynomial. And we're going to find all horizontal vertical asymptotes, and we're also going to find the domain. So starting with the horizontal asymptotes, we want to compare the degrees. And we notice that the degree is the same for the numerator and denominator. It's both to the second degree. So therefore, we're going to use the idea that it's going to be the ratio of leading coefficients, which would be 2 over 1. Notice there's no number here, so it's assumed to be 1. So the ratio is 2 to 1, of course, which is just 2. Therefore, our horizontal asymptote would be y equals. So it's y equals 2 is our horizontal asymptote. And now for the vertical asymptote, for that we look at the zeros of the denominator. The zeros of the denominator will tell us where this graph cannot exist. So to find the zeros, of course, you're just going to set it equal to 0. And this one should be easy to factor if you recognize different squares. And so the zeros are going to be the values of x that cause each factor to be 0. So for the first one, -1. For the second one, +1. So therefore, the vertical asymptotes are going to be vertical lines, and vertical lines are of the form x equals a number. So we will have, of course, x equals -1 and x equals a positive 1. And if you look at the graph, we'll just look at the book's version of the graph. And notice when you see a computer-generated graph, you don't see the arrows on the graph, but when you do it by hand, you should put the arrows on to show that the graph does continue in that direction. So that would be the graph, which supports the fact that y equals 2 is our horizontal asymptote, and then we have two vertical asymptotes at x equals -1 and x equals positive 1. All right, now the domain, and we also wanted to find the domain. The domain is basically going to be all real numbers except where we have that problem, and that problem is the vertical asymptotes. So this graph is defined anywhere except where we have those vertical asymptotes. So it's anywhere except -1 or positive 1. So when we read the intervals, we always read them from left to right. So that would actually be the interval from -infinity to -1, union with -1 to 1, which would be that point in between the two asymptotes, or that interval between the two asymptotes, and then, of course, union with 1 to infinity. So everything to the left of -1, everything between -1 and 1, and everything to the right of -1. Notice the parentheses means it does not include those endpoints. All right, let's look at one more example. We're going to look at this one here, where they want us to find the horizontal and vertical asymptotes, and also the holes. Holes are something that can come up in a graph when you have things that can be simplified. So this is our function. It's this polynomial over this polynomial, and of course they also want us to find the domain as well. So first thing I want to do is factor the numerator and factor the denominator. When I factor them, I see that they do have a common factor. Therefore, that common factor can be canceled out. What ends up happening, though, is since they cancel out, this doesn't change the shape of the graph, but it doesn't negate the fact that x is not allowed to be -2 in the original function. Because if x was -2, then we would have division by 0 on the bottom, even though we were able to cancel out later, we still have this as being our original function. And when that happens, we have what's called a hole. So there will be a hole at x equals -2. This is not, unlike an asymptote, this is not going to bend the graph and have it approach the asymptote. This will just be a single hole, single discontinuity, somewhere on the graph, which will be at x equals -2, and then to find exactly where, we can go ahead and substitute the -2 into our simplified equation, and if we replace x with -2 and do the arithmetic, we're going to get 3/5. So therefore, the point -2, 3/5 does not exist on the graph, even though everything else left and right of it does. So this is exactly where the hole will be, at -2, 3/5. Now for a horizontal asymptote, again, we're comparing the degrees, and since the degree is the same, then we're going to compare the ratios of the leading coefficients, which would be 1 over 1, which is 1. Therefore, our horizontal line is y equals, so it's going to be y equals 1 is our horizontal asymptote. And of course, for the vertical asymptote, again, we're looking for zeros of the denominator, but we want to find the zeros after we do our cancellations. So it's zeros of the denominator after cancellations for the vertical asymptotes. The zeros of the denominator that got canceled out, those were holes. So here we have x equals 3 would be the only zero of that denominator. It's the value of x that causes that factor to be 0. And if we look at the graph now, we'll see that the graph has that vertical asymptote at x equals 3. It has that horizontal asymptote at y equals 1. And then we have the two branches that approach the asymptotes as they go to each side. And at this one point here, now I know I drew it with a solid red dot because it's a little small. You wouldn't be able to see it as an open circle. But this would be a little small open circle on the graph. Everything else would be a solid continuous line, but that would just be an open circle on the graph to show that there's a hole at this point. Now, as far as the domain would be all real numbers except where we have a vertical asymptote, and also except where we have a hole. So here we would have our domain would be negative infinity up to negative 2, where the hole is, and then from union with negative 2 to 3, where the vertical asymptote is, and unioned with 3 to infinity, which is everything to the right. Alright, so being able to analyze these is good. We also need to be able to graph them ourselves. And now we've seen the graphs of a couple of these, but let's see how we're actually going to graph these ourselves. And there's a few steps we can do, some things we can do a little detective work. So let's say we have some rational function f of x. It's a polynomial over a polynomial. So n is going to be our numerator and d is going to be our denominator. And let's just take a look at some of our steps. First of all, we're going to simplify if possible. Factor the top, factor the bottom, see if there are any cancellations. And then any restrictions on the domain, in other words, any values of x that are not allowed because it would cause division by 0, you should list those, because even if they get simplified out, then they still are restrictions on the domain of the original equation. Next, we want to look at the y-intercept. We're going to plot the y-intercept, and that's a pretty easy process. We just substitute 0 for x. In other words, we're finding f of 0. And when we plug that in, we're going to get the value of y, which will be the y-intercept. So we want to plot that point on our graph. We'll start with that. Next, we want to find the zeros of the numerator. And that's by setting it equal to 0, and those are going to be the x-intercepts. X-intercepts are the value of x that causes the numerator to be 0, because that would cause the function itself to be 0. It doesn't matter what the denominator is. If the numerator is 0, then that function is going to be 0 at that point. So then we want to plot the x-intercepts onto our graph. And then next we're going to look at the zeros of the denominator. The zeros of the denominator are going to cause vertical asymptotes. So we're going to set the denominator equal to 0, solve for x, and then with dashed lines, dashed vertical lines, we're going to graph the vertical asymptotes. And also, if we had any that were canceled out when we simplified, we also want to spot those as being holes with open circles. And then next we want to sketch any other asymptotes by using graph lines. That would be horizontal asymptotes or oblique asymptotes. And then we want to plot at least one point beyond each x-intercept and between and beyond each x-intercept and each vertical asymptote. We want to see what's the behavior between those important features of the graph. And then finally, using a nice smooth curve, we're going to complete the graph by basically going from those known points, and we're going to approach the asymptotes in the proper directions. And we'll see that when we graph our next example. And of course, make sure not to plot any points where f is not actually defined. We can approach an asymptote. You can't actually reach a vertical asymptote. You can't actually touch a vertical asymptote with your graph. All right, so let's look at our first example. We're going to sketch the graph of this rational function. And for this, we first want to look at factoring. The numerator doesn't need to be factored, but we're going to go ahead and factor the denominator. I want factors of -2 that add up to -1. That would be -2 and +1. And this will allow us to easily find the zeros of the denominator. And we can also see that our y-intercept is going to be 0 because f of 0 is 0. If x is 0, the numerator is 0. And then it doesn't matter what the denominator is as long as you don't have division by 0, which we won't. then you'll have f of x is 0. So there's actually our first point. The y-intercept is actually the origin, so I'm going to plot that point. So I plot that point there. And next we're going to look at the x-intercept, which is the value of x that causes the numerator to be 0, and that actually is the same spot. So the origin is both an x and a y-intercept. And then next we want to look at vertical asymptotes. Those are the values of x that cause the denominator to be 0. So 0 as the denominator would be the value of x that causes each factor to be 0, which would be -1 for this factor, and +2 for that factor. So along the x-axis, we're going to have a vertical line going through x equals -1, and so I'm going to make a dashed line through -1, and then a dashed line through +2. And those would be my two vertical asymptotes. Next, I want to look at horizontal asymptotes, and this is actually going to be the x-axis. It's going to be the line y equals 0, because if you compare the degrees, we have a first degree polynomial in the numerator and a second degree in the denominator. So the denominator has a larger degree. Therefore, it doesn't matter what the other numbers or variables are in there. It's going to approach 0 as the numbers get large. So that is simply the x-axis will be a horizontal asymptote. Now for the x-axis, you don't need to draw a dashed line because that line is already there. You just need to recognize that it is an asymptote. That's why we're listing it here. All right, next we want to now just plot some additional points. And we want points between here, and to the right, and to the left. So if we look to the left, if I plug -3 into the function, I'm going to get -0.3. So -3, -0.3 gives me a point right there. At -1, we're undefined. So I want now from the origin, as I go to the left, approaching this asymptote, I might either approach it upwards or I might approach it downwards. I could go increase without bound, or I could decrease without bound. To find out which, we're just going to plot a point. So if I take -0.5 as my x, then my y turns out to be 0.4, which gives me this point there. Likewise on the right, I don't know, am I going down, am I going up? So to find out which, I substitute in 1 for x, and I find out I get a -0.5 for my y, so I plot that point. And finally to the right, if x is 3, I can plot my point. It would be approximately 0.75. So now I can see that from this point, let's start with this point, as I go to the left, my end behavior is going to be approaching the asymptote. So that would look like this. Just from that point, I'm going to the left. I put the arrow on because it will keep on going. And as I go to the right, I'm either going to be coming down or I'm going to be going up. I could plot another point, but if you think about it logically, anything less than 2 for your x, if I have something less than -1, anything to the left of -1, then looking on here, less than -1 would make the top would be a negative number, the numerator would be negative, and then less than -1 plus 1 is still going to be negative, and -1 minus 2 is, or anything more negative, minus 2 is still going to be negative. So you're going to have 3 negatives is a negative, so I know my graph will always be negative to the left of that asymptote. So that's why it's definitely going downward as we're approaching the asymptote as opposed to going upward. To the left of that asymptote, we're never going to have a positive value, so I know it has to come downwards. Now, starting at the origin, I see that going to the left, I could have went up or I could have went down. But since I found that point, now I know that I'm definitely going up as I go to as I approach that asymptote from the right. I will be going upwards, increasing without bound. Likewise, as I approach this asymptote from the left, because I have this point down here, I will be going downward as I approach that asymptote. So from here, approaching the 2 from the right, I either go up or I go down. But if you think about any number greater than 2 was going to be positive on the top, positive here and positive here, so it's always going to be positive. So it'll approach upwards there, and to the right, we know the end behavior is going to approach the horizontal asymptote. So that would be the process, or the thought process, of graphing that rational function. And when we compare it to the book's answer, or the book's graph, we see that we get the same graph. Again, notice how a computer-generated graph doesn't put on the arrows, but we always do when we graph it by hand. And we see that our graphs match. All right, let's look at one more example that has an oblique asymptote. So looking at this example, we have this function has a second-degree polynomial on the top and a first-degree polynomial on the bottom. Notice how it's not going to have a horizontal asymptote because the degree on the top is larger, but it is going to have a slant asymptote or oblique asymptote because the numerator is exactly one more degree than the denominator. All right, so starting with our first analysis, of course, we're going to factor the numerator. We get x minus 2 times x plus 1. So we can start out with finding that slant asymptote, because that's really what we're mainly focusing on with this problem. To find a slant asymptote or a horizontal asymptote, you're actually going to use long division. So we're going to do the long division here, or you could notice that the polynomial you're dividing by is a linear polynomial, so you could use synthetic division here as well. But your result is just going to be x, and then 2 is going to be your remainder. So it's 2 out of what you're originally dividing by. So this is the result of the polynomial long division. Now, any remainder, we can completely ignore the remainder as far as the slant asymptote is concerned, and you look at everything to the left, the whole polynomial to the left. Now this one turns out just to be x, but you're looking at basically the linear polynomial to the left. It could be 3x plus 5 or anything else that results in a line. So again, that x itself is the slant asymptote, so it's going to be the line y equals x. And y equals x, if we plot that as a dashed line, that would be our slant asymptote. And now we're going to look at the y-intercept. And of course, we're just plugging in 0 for x, and then we evaluate it, and we're going to get f of 0 equals 2. So that means when x is 0, y is going to be 2, and we're going to plot that point right there. That's our y-intercept. For x-intercepts, we want the zeros of the numerator, and we can look at the factored form to make that easier. We're going to have a positive 2 and a negative 1. So these are our two x-intercepts. So at negative 1, we have an x-intercept. At positive 2, we have an x-intercept. And we have 2 more points on our graph. Next, we're going to realize that the vertical asymptotes are going to be the zeros of the denominator, which in this case is just 1. The value of x that causes the denominator to be 0 would be 1. So the vertical line x equals 1 will be a vertical asymptote, and I draw that with a dashed line. And now for the horizontal asymptote, we mentioned earlier there is none because the degree of the numerator is larger than the degree of the denominator. So there are no horizontal asymptotes, but there is a slant asymptote or oblique asymptote at y equals x, which we've already put on the graph. So all that's left is we can plot a few additional points. Let's pick a point to the left here, which would be negative 2. If I put that in, I get a negative 0.133, which is 1.33, which is about there. If I have between these two, if I have x being 0.5, I get a value of 4.5 for y, which would be up there. So this side of the graph is pretty easy to figure out. As we come from this point to the right, we're going to be going up, so that is going to go up from this direction. And going to the left, we're going to be approaching the asymptote, so it's going to go through our point there and approach the asymptote to the left. And to the right, we can look at a point between here. If x is 1.5, when we substitute it in, we get negative 2.5 for that value. And if x is 3, then we would get a value of 2. So again, that gives us a nice curve through those 3 points. We're going to have going off to the right, it's going to approach the asymptote that way. And going off to the left, it's going to approach that vertical asymptote downward. And that would give us our complete graph. And when we compare this to the book's answer, we see we have, again, the correct graph. All right, that's it for the notes for rational functions, and we're done.